In this video, I want to introduce Coulomb's law, which gives the force that two charges exert on each other. Now, this will have both a magnitude part and a directional part. Both of these are necessary to understand Coulomb's law. Okay, so imagine that we have 2 point charges, Q1 and Q2, separated by a distance r. Q is a common symbol for electric charge. Now, by point charge, I mean that all the charge represented by Q1 is at this point, all the charge represented by Q2 is at this point right here. So well-defined points. That's what I mean by point charges. Okay, so we have charge 1 and charge 2 separated by a distance r. The magnitude portion of Coulomb's law says that the magnitude of the force that charge 1 exerts on charge 2, or also the magnitude of the force that charge 2 exerts on charge 1, is proportional to each of the magnitudes of each of the charges and inversely proportional to the square of the distance between the charges. And there's a proportionality constant known as the Coulomb constant, which has this value, 8.99 times 10 to the 9th newtons times meter squared divided by Coulomb squared, where the C represents a Coulomb. That's a capital C. That's the SI unit of electric charge. Note, a Coulomb is an enormous amount of charge. In comparison, 1 proton has a charge of 1.60 times 10 to the minus 19 coulombs. We use E for the charge of a proton because that's also the absolute value of the charge of an electron. Great. All right, so this gives the magnitude of the force that charge 1 exerts on charge 2. It also gives the magnitude of the force that charge 2 exerts on charge 1. Now, we also have a directional aspect. If charge 1 and charge 2 have the same sign, those charges repel. If they have opposite signs, they attract. It doesn't matter if this one's positive and this one's negative, or if this one's positive and this one's negative. As long as the signs are opposite, they'll attract. Great. Note that overall together, this is consistent with Newton's third law. These charges exert the same strength of force on each other, but always in opposite directions. We'll never get a situation where the forces that they exert on each other are like this or like this. They'll always be like that or like that. All right, so this is the magnitude portion of Coulomb's law. This is the directional portion of Coulomb's law. There's a couple more things I want to say. One thing I want to say is that sometimes you'll see this written in another form. Instead of seeing this k sub E constant here, you'll have it replaced by 1 over 4 pi epsilon naught. Epsilon naught is just a different physical constant. It's obviously related to the Coulomb constant, but epsilon naught has the value 8.85 times 10 to the minus 12 Coulomb squared, capital C again, divided by Newton's meter squared. Sometimes you'll see epsilon written with a slightly different symbol. This is known as the permittivity of free space, and you can look that up in any textbook. All right, great. One more comment regarding notation. Often I'll leave the E off this subscript K. So sometimes when it's clear that I'm referring to the Coulomb constant, I won't bother to write this E subscript. So in many of my materials, I'll just have a K here. Another thing, 8.99, that's really close to 9. You could just use 9 here instead of 8.99, and you'll only make a mistake by about 1 part in 1,000. That's good enough for most of our calculations. So it makes this a nice, easy number to remember. All right, one last remark. You can also use this equation for cases where you don't have point charges, and it'll be an approximation. So the closer this charge is to being confined to a point, and the closer this charge is to being confined to a point, the more exact this formula becomes. The further away from a point you have, it becomes less exact. And then it becomes also a question of what you use for the R. So if you've kind of got a fuzzy ball here and a fuzzy ball here of charge, you can maybe take R between their centers, and you'll get an approximately good relationship. Now you could always be more exact by saying, well, this fuzzy ball of charge consists of a bunch of little charges, and this fuzzy ball of charge consists of a little ball of charges, and take care of all the different pairs exactly, so you can always in principle conceptualize it as being based on pairs of point charges. So you can always revert in some level to an exact description. One last thing, there are some interesting effects that come about when you have extended amounts of charge rather than confined to a point. Those things involve interactions with overall neutral objects. I've got a little asterisk here to remind me that we'll talk about that in a later video. All right, so hopefully this introduction to Coulomb's law is helpful. This will be the basis of a lot that we do in the coming week or two. Thank you.